People have pondered the issue for many years, what a different version of life might be like in other universes. Thanks to the James Webb Space Telescope, the most impressive instrument ever developed, this inquiry may finally be ripe for thorough examination. Taking into consideration Proxima Centauri, the star system closest to us, which is located just 4 light years away, researchers have observed a number of distinct anomalies on one of Proxima B's planets. Artificial anomalies known as lights have captivated the imagination within conventional science. What, then, are they? Could these lights indicate the existence of sentient beings on that world? Take part in our exploration of the James Webb Space Telescope's provocative detection of possible city lights that could transform our understanding. Earth is, at this moment, the sole planet known to harbor life. Since early times, people have questioned whether life can be found elsewhere in the universe. To continue this quest, American astronomers Thomas Pearson and Jill Tarter started the pursuit of extraterrestrial intelligence in 1984, SETI. The objective aims to collect transmissions using radio waves from the sky. Radio frequencies travel great distances and, as a result, are more easily detected by the 40 radio dishes comprising the Allen Telescope Array in the Nevada mountains of California. So far, no definitive alien transmission has been discovered. The successful launch of the James Webb Space Telescope advanced that endeavor by permitting the examination of numerous distant exoplanets orbiting stars. Positioned roughly 1 million miles away from Earth and armed with incredibly delicate detectors, JWST promises groundbreaking discoveries. Some time ago, we knew of no planets outside our solar system. Now, over 4,000 exoplanets have been found circling various stars. NASA suggests the universe may host thousands more. The earliest hints of life beyond Earth may emerge via the detection of extraterrestrial vegetation. On its way to Jupiter, the Galileo spacecraft turned back toward Earth and observed what scientists call the vegetation red edge, a biosignature composed of red and infrared wavelengths reflected by flora. A continent akin to Earth, blanketed in forest, should exhibit a bold, recognizable red edge indicator. JWST will attempt to measure this red edge on distant worlds resembling Earth in the habitable's own surrounding stars, possibly revealing vital information about their atmospheres and underlying processes. As starlight passes through a planet's orbit, JWST might detect missing spectral bands via spectroscopy. Specific wavelengths absorbed by molecules produce a unique pattern JWST can identify. This strategy may reveal atmospheric makeup and hint at biological viability. Life could inhabit Earth-sized planets with atmospheres similar to ours composed of oxygen, nitrogen, and carbon dioxide. By searching for uncommon chemical markers, we might be able to locate intelligent life. For example, industrial compounds like chlorofluorocarbons (CFCs) used in cooling and sanitizing would almost certainly be detectable from afar in Earth's atmosphere. Should JWST detect CFCs on an exoplanet, it would be convincing proof of technological advancement. Nonetheless, life on other planets might not resemble organisms found on Earth. Typical extremophiles microbes that thrive in dangerous environments suggest the majority of life may appear alien. These entities can withstand harsh conditions, such as temperatures up to 250 degrees Fahrenheit or strong acids with a pH below 3. Since Earth-like planets are more likely to support life than extreme environments, focusing on the most favorable candidates seems prudent. Water could remain liquid on such worlds if they orbit stable stars. Our Sun, a yellow G-type star, provides moderate light and has a relatively brief lifespan compared to the more numerous red dwarfs, which shine dimmer and cooler. These longer-lived stars offer extended time frames for life to originate and evolve complexity. Approximately 40 light-years away, JWST has targeted the TRAPPIST-1 system. This quiet red dwarf houses 7 rocky planets, 3 of which lie in the habitable zone and may harbor liquid water despite the star's smaller, cooler nature. One TRAPPIST-1 planet emits light in wavelengths somewhat akin to the sun's rays during the day. However, the most auspicious candidate for detecting city lights from outer space remains Proxima Centauri, a red dwarf 4.5 light-years away. Dimmer than our Sun, it demands much closer planetary orbits to sustain liquid water. In August 2016, astronomers identified a planet of approximately 1.3 Earth masses inhabiting the star's Goldilocks zone, known as Proxima B. It may or may not possess an atmosphere. Orbiting just 4.6 million miles from its star, it is exposed to powerful stellar winds that could strip away its gaseous envelope. Nevertheless, Proxima B receives sufficient star light for temperatures comparable to those on Earth. Due to tidal locking, it permanently faces its star from one side, similar to how the Moon faces Earth. Proxima Centauri is about 18% as massive as the Sun and emits only 5% of its brightness, which may render Proxima B a scorched desert. However, if the planet retains an atmosphere, liquid water might persist. In spite of the fact that it only receives 65% of the Sun's energy, Earth is happy. Proxima B, however, causes perpetual light and shadow due to its tidal locking, with dramatic thermal variation between hemispheres. It is also bombarded by Proxima's planets, receiving nearly 3 times greater energy radiation than Earth, including ultraviolet radiation and X-rays. Unless there is a magnetic field on Proxima B similar to Earth's protection, it is possible that life will be hard. Yet, if support exists for atmospheric retention, the planet may be more welcoming than thought. Sadly, models indicate that exoplanets with tightly locked systems may lose volatile gases as they expand onto the cold side. Earth's atmosphere, on the other hand, is replenished by volcanic activity, while robust magnetospheres assist in stopping escape. Without precise data on Proxima B's magnetic field strength, volcanic activity, or atmospheric presence, conditions remain uncertain. Nevertheless, due to a possible combination of surface liquid and atmosphere, the hope persists that Proxima B could sustain life, conceivably even a complex biosphere. Solar energy arrays could, in theory, block out sunlight on the hemisphere, generating electricity and illuminating the dark side to maintain a living environment. Getting to know Proxima B has sparked interest in whether it moves across its star from Earth's viewpoint routes that would make possible the measurement of its mass and size, thus revealing density and confirming rocky composition. During a transit, starlight could penetrate its atmosphere, but there are only about 1.5% chances that the orbit aligns to produce transits visible from Earth. Additionally, the star's flare behavior is erratic, complicating observation. Astronomer David Kipping of Columbia University notes that Proxima Centauri is highly unstable. Solar eruptions heat rocky worlds and produce infrared radiation remission. Still, rocky planets in such systems emit specific infrared signatures, and the JWST was designed to capture that radiation. The Proxima B footprint in infrared could reveal atmospheric traits. With infrared capability vastly surpassing Hubble's, JWST can even detect lights from outside faint ones on Proxima B's night side if they occupy a smaller frequency band than the star's glow. Proxima B's dayside may be covered in reflecting photovoltaic panels, redirecting starlight. This pattern of never-ending daylight and stark nighttime contrasts could reveal much. If there is no atmosphere, the dayside radiates absorbed energy as blackbody emission, while the night side remains frozen. Lesser daylight-nighttime temperature disparity could signify atmospheric presence. JWST needs only about 11 point-to-Earth days to gather sufficient data to detect potential artificial illumination on Proxima B's dark hemisphere lights that could hint at intelligent life beyond our solar system. In light of current analyses, Proxima B may conceal hidden revelations. Its sunlit side potential, paired with enduring night side illumination, might point to a society with advanced technology. While the prospect of artificial lighting on Proxima B would be revolutionary, scientists remain cautious. Such signals may originate from geological processes, volcanic outgassing, lightning, atmospheric electricity, or other peculiar weather events that mimic civilization. Rigorous research and validation are crucial. The JWST will keep an eye on Proxima B and other potential exoplanets that could support life, enhancing understanding of their atmospheric and surface environments. If artificial lighting is indeed noted, confirmation would necessitate years of monitoring to determine its origin. Should such signals derive from intelligent activity, it would rank among the top 10 most significant scientific advancements in human history. The enthusiasm for Proxima B and exoplanets originates not only from the pursuit of life, but also from greater implications for philosophy regarding humanity's function in the universe. Discovering extraterrestrial cultures would alter our perception of Earth's singularity. It could inaugurate a new era of global cooperation and unity, humanity bound together by shared curiosity and wonder, with compelling investment in new technologies to advance cosmic exploration. Currently, the search on Proxima B for city lights represents a tantalizing possibility, one that may soon indicate whether or not we truly are alone. As JWST continues to transmit new data, the goal of detecting intelligent life beyond Earth becomes progressively more observable, bringing us closer to solving one of science's most profound questions. Whether Proxima B shelters an advanced civilization or not, the very search might unlock the future of dialogue and exploration across the stars. In pushing the frontiers of possibility, the young astronomers, researchers, and explorers of the future may be the ones to confirm that what once seemed impossible given the diversity of life forms may, in fact, be more common than ever imagined.